All right, everybody. Day number 4. You review some Euler's method. I'm not going to do that in this video. I'm going to talk about the homogeneous method for finding a particular solution. Now, it's not like Euler's where I'm estimating some value for y. I'm actually finding the function. Kind of like separation of variables in a different way. Okay, so homogeneous expression for dy dx looks like or can be altered to a single term to work for separation of variables. Right, so this right here, example 1, is not homogeneous because I have addition of two terms, right? But this I can write and will be able to using the method we're about to do in a moment here. I can write separable. And the method that we use here is we do a u substitution. Okay, u is equal to y over x. If we use that substitution, we've got some stuff we can do with this, and we can separate and integrate, and then translate. After we're done with u, we can translate it back to y and x. I'm going to show you that in an example on the next page. Okay, so before I get into these examples, what I'm going to do is I'm going to help us to come up with our friend here that we're going to use throughout any sort of homogeneous method problems here. So if u is equal to y over x, then y is equal to ux. And because we have a dy dx, I want to find out what that would be in terms of u and x. So if I took the derivative of this with respect to x, I would get that dy dx is equal to, and I'd have to use product rule here, I'd have du dx times x plus u. So I'm going to be using this right here as a direct substitution for dy dx as I go through a couple of these problems. Okay, so check it out. Here's what I got. I got dy dx equals x plus y over x. So really dy dx equals 1 plus u. Okay, all I did was split this up to x over x plus y over x. And now I need to do my substitution, right? Because I've got dy dx, I want du dx. Recall that dy dx equals du dx times x plus u. Clearly, if I subtract u from both sides, I would get that. So du dx equals 1 over x, right? I just divide by x. Oh, bad color choice. And now what I have is I have du equals 1 over x dx. And I can integrate. Now, I'm going to integrate on both sides, on the left with respect to u, on the right with respect to x. And I'll get u equals natural log of x. And instead of putting plus c on both sides, I'm just going to put plus c on the dx side, right? Plus c. And recall that u equals y over x. Therefore, I'm almost done here. I would just have y equals x times natural log of x plus c. Now, I didn't have an initial condition, I don't believe. Nope. Therefore, I would be done right here. This would be my general solution to that differential equation. Okay, so let's try this one. Dy dx, I'm going to split this again, would be equal to u squared plus u. Now, how did I get u? Well, I think you could probably see how I get u squared. That's how I got u squared. How I got u was that x here would cancel with one of the x's here, leaving me with y over x. So recall that dy dx is equal to du dx times x plus u. Again, the u's cancel here. So du dx times x equals u squared. Okay, so now I have a separable equation here. If I were to multiply both sides by divide both sides by u squared and divide both sides by x, I would end up with du dx times 1 over u squared is equal to 1 over x. Right, these would cancel here and there. Right, so now I can separate here real quick. 1 over, let's call that u to the negative 2, du equals 1 over x dx. Integrating both sides, I get negative 1 over u is equal to natural log of x plus c. All right, so what is 1 over u? Well, 1 over u is equal to 1 over y over x. Therefore, 1 over y over x is equal to negative x over y. Okay, so this is where it gets kind of funky. All right, let's change these for a moment. Let's change it to a positive, which would make everything over here negative. Okay, now if I take and I make everything over here negative, that'd make that negative natural log, and c would just still be a constant, so I'm going to say plus c. Okay, I'm going to then multiply everything by y. Okay, so then I'd have x is equal to, I'm going to write this as the natural log of 1 over x instead of negative natural log plus c times y, and therefore y would equal x divided by the natural log of 1 over x plus whatever our constant is. All right, you guys, those are the first couple of examples of this homogeneous method. Let's try another. Okay, let's do this one from the homework and we'll call it good. Use the substitution y equals ux, we know that, to show that the differential equation x dy dx, right, x dy dx is equal to y squared plus x squared plus y. Okay, so, and show that it can be reduced to this thing. Okay, so what I'm going to do is first divide everything by x. So dy dx will equal, okay, y squared over x will be ux, right? X squared over x will be x, and y over x would be u. One mistake I made in my logic here is this first term would be uy. So now I'm going to do my substitution for dy dx. Recall that dy dx equals du dx times x plus u. That'll be equal to what we have over here, uy plus x plus u. These u's will cancel. Then we're going to divide everything by x. And therefore, du dx will equal, this first term will be u squared, and the second term will be plus 1. All right, so we've shown that that can be reduced. Du dx can be reduced to that. Hence, show that the general solution is given by the following. Okay, so this is a really cool one. You might not think this is separable, but it absolutely is. Du dx, oops, I'm going to say du equals u squared plus 1 dx. Now you're saying, how do I undo that? How do I get the u? I can't. What do I do with the 1? Well, divide by all of it. Okay. And what does that look like? That to me, right, I have the integral of 1 dx, and over here I have the integral of 1 over u squared plus 1. That looks like arctangent to me. All right, so this would be the arctangent of u is equal to x, excuse me, plus c. All right, so if I were to undo arctangent, that would be tangent of both sides. So u would equal the tangent of x plus plus c, and u is equal to y over x. Therefore, y would equal x tangent of x plus c. Let's see if I got that right. And we did. Awesome. There's our general solution to that differential equation. All right, you guys, that's homogeneous method. Peace out.